Hello everyone and happy Halloween. Today, for our Halloween special, a NASA scientist finally goes on record about the truth behind sprites, gnomes, pixies, elves, trolls, and more. Of course, we're not talking about the mythical creatures of the forest, we're talking about the colorful lights that sometimes appear high in our upper atmosphere above thunderstorms, more commonly known in scientific parlance as transient luminous events. I'm Miles Hatfield, NASA science communicator, and I'm here with Burju Kosar, NASA scientist and expert on these mysterious electrical phenomena. Burju is starting a brand new project called Spritacular that aims to open up this exciting field of science to broad public participation. We're here to talk about that project and the ghostly figures that it studies. So first off, what are sprites and some of these other things that I mentioned at the top?
So sprites, also known as red sprites due to their dominant red color, are upper atmospheric electrical discharges of air that are connected to thunderstorm systems below. So what I mean by that is every sprite event, in a way, have a parent lightning flash. So they're tightly connected in a way. They happen at about 50 miles up in our atmosphere, and they have complex morphological features. What I mean by that is they come in various shapes and sizes. Some of them look like a carrot bunch just pulled out of the ground. Some of them look like columns. Some of them look like angels. And the most fascinating one is actually called dancing sprites. They almost flicker like a little light show about the thunderstorm systems. And also we do not really currently understand how they take the shape they do or why they take the shape they do. It is a very least understood field of research.
How big are we talking? How rare are they? How hot or cold are they? If you can give me more sense of what sprites are like.
So what I would say is they are not like the hot lightning bolts. They are relatively cold. Their home is the coldest layer of the atmosphere, which is the upper sections of the mesosphere. So they're formed by these filamentary plasma channels called streamers. They are weakly ionized channels, so they are cooler in comparison to the lightning bolt itself. They're relatively rare. To be able to make them happen, we need very powerful positive cloud to ground lightning flashes. So what are these positive cloud to ground lightning flashes? They are very powerful flashes. They transfer the positive charge from the cloud to the ground, and they are responsible for generation of sprites.
So why have I not heard of sprites before? Are they very rare? Why don't most people know about these?
So I would say it's a relatively new field of research. This field of research started in 1990s when a group of scientists were testing a low light level TV camera for an upcoming rocket mission, and there must be a thunderstorm relatively nearby, and they captured sprites on record for the first time. When they reviewed their footage, they saw these two massive luminous blobs extending about the active thunderstorm systems. And that is actually the first milestone image that kickstarted this field of research in atmospheric and space electricity. After that, there has been many campaigns started to catch them and study them. There were ground-based campaigns, there were aircraft campaigns. The reason aircraft altitude is very, very good to study or look at these phenomena is the vantage point. When you're flying around the nearby thunderstorms, you have this great view of the top of the thunderstorms, which is home for these phenomena that we refer to as transient luminous events. So another important thing to mention here is this field of research is actually no stranger to citizen science. Because when you look at some of the historical anecdotes, people have been describing sightings of these strange flashes of lights about the thunderstorm, almost going back to hundreds of years. Even pilots were seeing them. But what they see is actually just a flicker of light. They do not see these phenomenal detailed images that are shared on the internet. So that is a still capture ripped off of a video footage. So they are very, very fast. So to the human eye, they're almost like a flicker of light, like a flash of light. And it is very hard to perceive color. So people, when they look at the aurora, they see these green arcs moving in the sky. For sprites, unfortunately, that is not possible because they are very brief and very fast. They are visually beautiful in the still photographs.
So it sounds like you've seen some sprites in person before. Can you tell me what that was like?
So I wouldn't say I have seen it. I have captured it on camera about a year ago. I have been studying sprites for about 15 years now. I did my research work during my PhD. And like I said, it was an opportunity. We recorded a sprite chasing documentary down in Oklahoma. I had the opportunity to work with one of the phenomenal sprite chaser, Paul Smith. And we went and we chased a bunch of storms that was over a nearby state. And we were lucky enough to capture a sprite on camera, and it was actually column sprites. It was a great experience, I would say, because that kind of, in a way, made me realize how knowledgeable citizen scientists are, and the amount of information that we can exchange and collaborate and advance this field of research was really, really great. And that's why I'm thinking this project of mine that is going to be launching this month is definitely a very worthwhile effort, and I'm so excited about it.
Good. Tell me more about what Spritacular is. You mentioned citizen science, but what does that mean, and how can your average person get involved in something like this?
Yeah, so Spritacular is NASA's brand new citizen science project. So citizen science projects are, in a way, collaboration between professional scientists and the members of the public. So it is almost like an exchange of information. So as a scientist, I look at a lot of scientific data. I study the physics of this phenomena, and scientists are very knowledgeable about these. And we look at satellite data. But when you look at the public and sprite chasers, they are phenomenal photographers. And not only that, they are very knowledgeable about what they are doing. They're almost, it would be wrong to call them amateurs. They're extremely talented. So they capture these phenomena and they want to learn more about what they're capturing and what these things are. So that's where this project will come in. We want to create a bridge between these two communities and enable exchange of information for the advancement of science collaboratively together. So the way people can participate in this project is, I would say, if you live in a place where thunderstorms frequently happen, and if you happen to own a DSLR camera, and if you're a little bit patient, and if you like to go outside at night and watch the night sky, this is actually an excellent project for you. I would say the hardest part of catching a sprite is knowing where to look. But there will be a wealth of information on our website, spritacular.org, where you can come and learn about these phenomena. And if you happen to observe sprites or any other TLEs, you can submit your observations to our database, which will be used by the scientific community for research in the future. So long story short, if you are passionate about thunderstorms, if you have some patience and a off-the-shelf DSLR camera, you're off to a great start to capture these events.
This raises a good question. I mean, probably most people who know about NASA, they know that we've got all kinds of satellites, we've got all kinds of equipment that we use to make observations of the night sky. What makes a person with a camera on the ground so useful for these sorts of questions that you're asking?
So because these events occur in a specific region of the atmosphere, as I mentioned earlier, the best vantage point to observe them are from aircrafts or locations where storms happen frequently. From the orbit, satellites see them, but it's very hard to resolve the details of these phenomena. The ground observations give us an excellent vantage point to see the details, and also they serve as ground truth for satellite observations. If we look at the satellite data to understand what we captured, and if we have a confirmation from the ground, that is an excellent source of data point, I would say. And with this project, we are going to be creating the first ever crowdsourced database of TLEs, which currently doesn't exist. So it is a very exciting endeavor. It will be open to every scientific community, and we intend to make this a global project because where powerful thunderstorms happen, you have a chance to see sprites and other TLEs.
So tell me more, what about these other TLEs? Obviously your project is called Spritacular. As I understand, sprites are the most common TLE that people are likely to see, but there's a range of others. Can you say more about what they are?
Yeah, of course. So the transient luminous events is the technical name the science community gave to refer to these optical emissions about the thunderstorms. So this region is almost literally like an electrical zoo. We have all sorts of different phenomena. Sprites are one of the, like you mentioned, one of the most commonly observed types, but we have halos, we have elves. Halos are almost like a diffuse glow, like in the shape of a pancake. Elves are in the shape of a donut that extends radially outward. And we have jets and gigantic jets which shoot up from the thunderstorm tops. Gigantic jets are so massive, they literally create an electrical bridge between the thunderstorm tops and the ionosphere, effectively coupling two different regions of the atmosphere. So these are some of the types of TLEs that we are interested in, including in our database for scientific research.
Where do they get these funny names from?
Yeah, that's a good question. So the first discovered TLE was sprites, and because of their elusive, fleeting nature, they were dubbed as sprites by late Dave Sentman. And after that, it kind of got stuck. And when the field of research got kicked off with this first observation, we started discovering more types. And I think the overall team sort of got stuck. Some of these names are actually acronyms, but I think scientific field has been a little bit playful with naming these optical phenomena.
So aside from making bright light shows and quick, momentary flashes, do these TLEs have any effect on people, on our Earth system as a whole? Are they dangerous in any way?
Yeah, that is a good question. So they happen, as I mentioned earlier, at about 50 miles up in our atmosphere. So they do not endanger us here on Earth, but of course they have effect on other Earth systems, such as the global electric circuit. So global electric circuit is the name that we give collectively to circulating currents in our atmosphere. So sprites and other TLEs, being electrical phenomena, they do carry currents. So they provide, in a way, feedback into this global electric circuit. I would say a thunderstorm, a lightning flash, or sprite or any other TLE is not an isolated event. It actually feeds back into this larger system that we call global electric circuit. And another thing to mention here, sprites locally affect the atmosphere electrically and chemically and modify its content. So what this does is this affects our long-range radio communication systems. And also the atmospheric chemistry changes that they do locally in the atmosphere, it feeds back into the atmospheric chemistry. So they do have global effects that we would like to study and understand further.
This stuff is fascinating. Thank you so much for joining me for this discussion, Burcu.
Thank you, everyone.
And before you all head out for trick-or-treating, there's much more to learn about transient luminous events. Burcu will be sticking around and answering your questions today, so leave them in the comments below. Thank you all for joining us, and happy Halloween!